So let's just revise a little bit for a moment. Transition metal chemistry. You've had transition metal chemistry, classical coordination transition metal chemistry from Dr. Claydon already on 2C32. And what I'm going to be talking about is organometallic transition metal chemistry, transition metals bonded to carbon ligands, carbon-based ligands. And the beauty of these species is we'll see they have new types of reactivity, new types of structure, unusual structures that you won't have encountered before. Even though I know you've seen Grignard reagents, you won't have seen some of the structural types that we're going to be talking out on here. And we're going to show, as I say, we're going to justify our existence as synthetic inorganic chemists by showing how useful these things are in stoichiometric organic synthesis, and more importantly, how useful these things are in industrial catalysis. Now, why then are these transition metal compounds ideally suited for forming organometallics? Why is it that transition metals form these novel organometallics in a huge variety of different patterns? Well, what we have to recognise, of course, is being transition metals, they do their chemistry with d orbitals, but they are not restricted to doing their chemistry with d orbitals. You can hybridise those d orbitals with the s and p atomic orbitals, and when you do that, you can adopt a very great variety of different coordination geometries and organisation of hybridised ligands. And those hybridised ligands have just the right symmetry properties to overlap with the orbitals of organic molecules. And as we'll say, there are examples where we have the classical ligand type behaviour that you will have encountered with Dr. Claydon, whereby the ligand is simply donating a pair of electrons to the metal and forming a sigma bond. But we will also spend considerable amount of time starting this afternoon looking at examples where d orbitals are overlapping with unoccupied orbitals on the ligands, anti-bonding orbitals on the ligands, and there we will see electron density being donated in the counter-classical direction from the metal to the ligand. And we'll look at examples of ligand types like that, pi acceptor species. So we can have interactions between both pi orbitals on organic ligands and pi star orbitals on these ligands. And of course, if you think about this very quickly, if you occupy orbitals on a ligand, so if you have electron density being donated from your ligand to the metal in the first instance, what you are doing is you're then decreasing electron density on your ligand. If you decrease electron density on your ligand, then you are going to make it more attractive for nucleophilic reagents. So if you make your ligand more positively charged, it is more likely to be attacked by nucleophilic reagents. Now, if you consider you have a situation where essentially what you are doing is you are donating electron density from the metal to the ligand, if you pump electron density into the ligand, then instead of making it more attractive towards nucleophilic reagents, it will become more attractive towards electrophilic reagents. And that's the basis of catalysis. You can change the reactivity of your organic substrate by coordinating it to your transition metal centre. Now, let's have a little bit of revision. Professor Botman, no doubt, would have talked about the Octet Rule, and I know that I talked about the Octet Rule extensively when I was talking, giving you the 1C3Y lectures. So let's remind ourselves, what is the Octet Rule? Well, the Octet Rule is a sufficient number of bonds are formed to surround the central element by an octet of electrons. In this way, the element reaches the electron configuration of the noble gas with the next highest atomic number. So that's our dictionary definition of the Octet Rule. And of course, we can take an example of that. So if you look at tin, tin is in group 14. It has 4 valence electrons. It forms 4 conventional covalent sigma bonds with methyl radicals to make a tetramethyl tin species. We encountered that in the last lecture. And tetramethyl tin is going to have an octet of electrons. And because it has an octet of electrons, first of all, we would predict it's going to form 4 bonds because that gives us an octet of electrons. It's got 4 valence electrons to use. But once you have an octet of electrons, then you can predict that a compound will be relatively stable. So in main group chemistry, we know we are aspiring to an octet of electrons. And if we can achieve an octet of electrons, we will have a relatively stable unreactive molecule. And that's the function of the octet rule in main group chemistry. Now, if we go to transition metal chemistry, we don't deal with an octet rule, we deal with something called the 18 electron rule. And if I read this out, a stable complex with the valence electron count of the next highest noble gas is obtained when the sum of metal d electrons, electrons donated from the ligands, and of the overall charge on the complex equals 18. So we're going to do exactly the same sort of analyses that we did in main group chemistry to arrive at an octet rule. We're going to count electrons in exactly the same way and see whether we fulfill this 18 electron rule in transition metal chemistry. And just as it allowed us to predict, firstly, what molecules are going to be formed and how stable they will be, the 18 electron rule has a very similar predictive and stability predicting role in transition metal chemistry. So it's a very powerful method for allowing us firstly to predict structures, because you'll see many cases where we can easily vary the number of ligands. And secondly, once we know what the structure is, to predict whether it's going to be a stable structure, a reactive molecule or an unreactive molecule. And so most of the transition metal compounds we encounter on this course will be 18 electron compounds. So of the numbers you've just torn out, I expect that the 18 will be the most thumbed one during the course. But there are other examples, and we'll be trying to see whether you spot those other examples and the consequences when you spot those other examples. How do we count electrons? Well, first of all, we said we're going to work with the number of d electrons. So you're used to this concept. What we need to do is we need to work out how many d electrons we have. And we're going to be doing what we call a covalent counting method. So we are not in the least bit interested in the oxidation state. Okay? This is a little bit in contrast to what Dr. Claydon had been doing, where ultimately what you want is the number of electrons in your ion. We are going to be counting the number of electrons, if you like, in our complex, not just our metal ion. So we're not getting at oxidation states at this point. We don't even need to work out the oxidation state in order to do electron counting. All we need is the number of d electrons brought to the metal complex by our metal center. And that, essentially, is the group number. So if you recall, and hopefully everybody has had this drummed into them, and so they're convinced by it, whenever you are doing chemistry, whenever you have a chemical environment in which you place your metal, under those circumstances, the 3d orbitals are lower in energy than the 4s. And therefore, they are filled with electrons first, through the Aufbau principle. The only time when 4s orbitals are lower in energy than 3d is when you have atoms in the vacuum phase. And we are not dealing with atoms in the vacuum phase on organometallic chemistry. We are certainly dealing with chemical compounds. So the d orbitals are lower in energy than the 4s orbitals. And so the number of d electrons is simply the group number. It is that simple. You look at the group number. If it's titanium, it's in group 4. If it's iron, it's in group 8. That is how many d electrons they've got. That's how many electrons they bring to our electron count. Now, as I just mentioned, we're using a covalent counting method. And what that means, we touched upon it briefly last week, what that means is that we are breaking or regarding bonds as being truly covalent. And when you imagine these bonds being broken when you're dealing with covalent bonds, then you break them in a homolytic fashion. So what we're thinking about are the metal radicals that are produced when you break bonds in a homolytic fashion, and the radical ligands that are produced when you break bonds in a homolytic fashion. So a chloride ligand bonded to a metal, if you break that bond in a homolytic fashion, you get a chlorine radical and a metal radical. The chlorine radical has one dot on it, is a 1 electron donor. So when you're using this covalent counting convention and regarding neutral ligands, then ligands that bond in a normal sigma fashion, as Lewis would say, by sharing a dot with a cross, those are 1 electron donors. So we have neutral radical ligands. And it'll become obvious exactly how we use those because we'll have plenty of examples to work with. And we must stress, it really isn't necessary to work out the oxidation states. Oxidation states we'll come back to right at the end of this lecture. Oxidation states are a very useful concept. They are absolutely not required in order to do the covalent electron counting method we are using. If you start trying to assign oxidation states whilst you are counting electrons, there is a danger of confusion. Keep the two things separate is my mantra and the advice that I'm giving you now. So what we need to do essentially is to recognise that the number of d electrons contributed by the metal in an organometallic is equal to the group number. It really is just that simple. Okay, and then of course we have to consider the ligands. Now this is a fairly imposing looking table to throw in this early in the course. What you have here is a summary essentially of all the material we're going to be looking at in the next 7 lectures or so. So these are the systems we're going to be working with, and the ones highlighted in magenta or pink, what do you want to call it here, these are the ligands that we'll be spending a bit of time on. The remainder of the ligands might feature in 3C32, or they may feature in the more extensive consideration in your textbooks, but all you would have to do is, or all you ought to be able to do, is just look at them and recognise how many electron donors they're going to be. So I don't really want to work through this table in any detail now, because we will be returning to this. Just to flag a couple of points at this stage, and that is these normal sigma donors that form covalent electron sharing bonds are 1 electron donors. If you have a ligand that doesn't form a bond through sharing electrons, it forms a dative bond. Any ligand that simply donates a pair of electrons to your transition metal, for example water, ammonia, carbon monoxide, these are dative donors to a metal. And so in those cases, when we break the bond, we regenerate a perfectly stable molecule with a lone pair of electrons. Those are 2 electron donors. So a ligand like a chloride is a 1 electron donor. A ligand like water is a 2 electron donor if you are using a covalent counting methodology. There are species where essentially what you do is you combine combinations of 1 electron and 2 electron donors. So they will see examples of a halide ligand bridging between 2 metal centers. That's a 3 electron donor in total. But there are other cases where, well, that's this example here, there are other cases where essentially 3 carbon atoms are bonded to the transition metal at the same time. And when you want to know if you have extensively conjugated organic ligands. So examples of extensively conjugated organic ligands, this is an allyl ligand. This is a diene ligand. This is a cyclopentadienyl ligand. If you want to know how many electrons those are donating to your ligand, actually it's quite simple. All you need to do is to count the number of carbon atoms. So an allyl has 3 carbon atoms, it is a 3 electron donor. A cyclopentadienyl ring has 5 carbon atoms, it is a 5 electron donor. And benzene has 6 carbon atoms and is a 6 electron donor. So it is a 1 electron donor for each of the atoms that's interacting with the metal. Now if you have an example of a diene which is non-conjugated, like this one, so this conjugated diene, all 4 of these atoms will be interacting. If you have a non-conjugated diene, which might have a lot of separation between the two, it is only the atoms that are bonded to the metal that you need to count. So this diene might have all sorts of organic flab in between here, but it will only be bonded through the unsaturated groups, so a diene is always going to be a 4 electron donor. Now, there is various nomenclature aspects that we need to get a grip on. One of these is the notion of prefixes. So there are a couple of prefixes that are used in this chemistry. The first of these is the prefix eta. And the prefix eta with a superscript n is the number, essentially the number of carbon atoms bonded to the metal, which I've just told you is equal to the number of electrons that it donates to the metal. Now, if you have a ligand like a cyclopentadienyl ligand, and we will come back to this, that is normally bonded face on in an eta 5 fashion. Wherever you do not see the value of eta, strictly speaking, the value of eta should always be stated. Whenever you do not see the value of eta stated, then you assume the highest possible value. And this value of the number of atoms bonded to the metal is also called the hapticity. So you may well encounter the word hapticity, and the hapticity of a ligand is the number of the carbon atoms, or in some cases others, but we're doing organometallic chemistry, so the number of carbon atoms bonded to the metal. So the hapticity of a cyclopentadienyl ligand is normally 5. It can be less than that, in which case I would definitely expect to see it specified in the form of this prefix. There's one more prefix that we need to use, and that is mu. Mu refers to bridging. So it makes absolutely no sense, and it would be entirely pointless to have a mu1, because essentially mu1 is bridging one metal, so it doesn't make any sense. It's a terminal ligand. So you will never encounter mu1. But if you have a ligand that is bridging two different metal centers, then that ligand will be described as mu2. Occasionally you will see a ligand that is bridging 3 metal centers. There, that ligand is a mu3 species. So that's what the mu nomenclature refers to. Now, we are counting electrons. Therefore, we need to consider the charge on our compound. If our compound is neutral, fine. If our compound is positively charged, what's that saying? If something is positively charged, then what have you done to the number of electrons? You've removed one. So if the species is positively charged, we need to remove an electron from our electron count. Now, equally, it follows that if a species is negatively charged, then you have added an electron and you need to add an electron to your count. So don't forget the charge on the complex. It is incredibly important and an easy way to slip up if you're counting electrons in these species. So let's do some examples. Hopefully we feel equipped to do some examples, and hopefully you have this slide in your notes. So this should be really easy. How do we do electron counting? What we need to do is we need to recognize the number of d electrons brought to the complex by nickel. And that becomes simply a question of which group in the periodic table is nickel. 10. That's the D10. So we're going to have 10 electrons from nickel. Now, a carbonyl ligand. You will have encountered carbonyl ligands to some extent, and we will talk about carbonyl ligands in some considerable depth in the second lecture today. But principally, how does a carbonyl ligand bind to a transition metal? What sort of a ligand is it? It's a sigma ligand. And all sigma refers to is the fact, essentially, that you've got cylindrical symmetry about your bond. So yes, you have a transition metal. Let's call it a transition metal here. That is a sigma bond. So you have a bond with cylindrical symmetry about the interatomic axis. But what sort of electrons is it donating? Is it an anionic species in a formal oxidation state type consideration, or is it a dative donor? Yes, okay, that's the word I was looking for. CO ligand is a dative donor. And if it's a dative donor, it is a 2-electron donor. So we have 4 CO ligands, and these CO ligands are going to be donated 2 electrons each, giving us a total of 8. 10 plus 8 is? Wow, okay, right. Next time I expect to see the little pieces of paper appearing. Now, let's take another one. Bis cyclopentadienyl iron. That's the formal name for this species. Anybody got any more names for that? I think at least one of you would recognise that. Yes, it's ferrocene. So this is ferrocene, and we will talk about ferrocene again at the end of this course. So I've already seen 1 or 2 students flashing some numbers at me. That's what we want. Let's do it systematically. Some of you will argue that this is a waste of time, but when you have a really complicated molecule, just like when you're assigning oxidation states, to have a method is very helpful. And what I would stress is when I'm marking examination papers, I am looking for how you arrived at numbers, because it's true. Most of the time, the answer will be 18. And you could just guess at that going into the question? Well, they won't all be 18. And when the answer is not 18 and you've got it wrong, what I will be able to do as an examiner is credit every statement that is correct. So if you correctly say that iron is in group 8 and will bring 8 d electrons to your count, then I can give you some credit for that in my marking scheme. If you correctly state that a cyclopentadienyl ligand is an eta5 ligand, so this is an example where I haven't specified the hapticity of the cyclopentadienyl ligand, and by default we are assuming it's its maximum value of 5, so we have Cp times 2, and it's a 5 electron donor, so this is going to give us 10 electrons. So it is once again an 18 electron compound. I have actually got some more examples like this on another slide, which you don't have in your handout, which will exercise these little numbers a little bit more effectively, because I know you have all these answers. Let's take this third example here. This is an 18 electron complex. You know that, you've got the answer in front of you. But what you need to be able to do is say it's an 18 electron complex because chromium is in group 6, therefore brings 6 electrons. A CO ligand is a 2 electron donor and we have 3 of them, making a total of 12 so far. And this C6H6 species is the C6H6 species, i.e. it is benzene. Benzene will bind in an eta6 fashion and be a 6 electron donor. So this again is an 18 electron compound. Let's have an example with a charge in it. This is vanadium hexacarbonyl anion. Vanadium is in group, which group is vanadium in? You probably don't have it stating vanadium is in group 5, but all the clues are on your handout. Vanadium is in group 5. So it's bringing 5 d electrons to the count. That's where that number has come from. CO ligand is still a 2 electron donor. So we have a total of 6 times 2, which is 12, plus 5 is 17. And so it's a 17 electron species? Well, not quite, because of course it's an anion, and we need to add 1 more to our electron count. And so all the examples on this slide are 18 electron complexes. Let's have another one. Okay, so there's your calculations. That's what it says on your handouts. Let's have some more examples. So, what is the electron count for iron pentacarbonyl? I have quite a few actually. Oh, very good. Yes, it's nice to see so many of you playing the game. Don't conveniently lose these things before the next lectures, because we'll be using them consistently throughout the course. Okay, brilliant. I haven't seen a wrong answer and I've seen a majority of you with the right answer. Yes, of course it's an 18 electron complex. Why is it an 18 electron complex? Well, iron is still in group 8, bringing 8 to our count. 5 CO ligands at 2 each is 10. 10 plus 8 is 18. So this is an 18 electron complex. Right, what about the next one? Bis cyclopentadienyl cobalt. Oh. Interestingly enough, we have a difference of opinion, but not... We do have a difference of opinion still amongst the audience, but what we don't have is anybody telling me that it is an 18 electron. That would be a bit tough, wouldn't it? Because we've already encountered bis cyclopentadienyl iron and found that that was 18. So clearly, actually, we can do this a number of ways, but if we recognise that the relationship between iron and cobalt. What is the relationship between iron and cobalt in the periodic table? Yeah, cobalt is one place to the right of iron in the periodic table, meaning it's got 1 more electron. So if it's got 1 more electron and everything else is the same, then clearly by that token the answer must be 19. So congratulations to everybody who's put 19. That presupposes we've just worked with ferrocene, which is not how you'd normally be in an examination. So in these circumstances, what we should be doing is looking at these and saying, well, let's do it systematically. So we have 2 cyclopentadienyl ligands at 5 electrons each, that's 10, plus cobalt, which is in group 9, is 19. So again, of course, it's a 19 electron compound. What about cyclopentadienyl cobalt dicarbonyl. Now, I would add at this point, one of the dangers that we get into here is that C(o), depending on what your handwriting is like, looks quite a lot like C(o). And I've recently marked a piece of tutorial work. Of course, it was anonymous, so I don't know who it was, but in that piece of tutorial work, I think it was actually first years, to be honest, but in that piece of tutorial work, there was an issue where the central element, in order to work out their isomers, was actually a carbon monoxide ligand, because there had been some confusion between cobalt and carbon monoxide. It is an 18 electron complex. How is it 18? Well, clearly we have 5 plus 2 times 2 is 9, plus 9 is 18. So that is an 18 electron complex. And finally, titanium hexacarbonyl dianion is an 18 electron complex. So it seems to me that after about 30 minutes of electron counting, you are all fluent in counting electrons. Okay, so there's our working here. Now, there are some additional factors that we need to do when we're counting electrons. And the first of all is we have to recognize that if we have an odd electron fragment, so if we have a species that has an odd number of electrons, for example, we'd be working with metal carbonyls. A carbonyl ligand is a 2 electron donor. And so we can't, if we start off with a metal which has an odd number of electrons, for example, cobalt. Cobalt brings 9 electrons. So we are never going to get to 18 by adding multiples of 2. It isn't going to happen. But what you can do is add 4 CO ligands to cobalt. Then you will get cobalt's tetracarbonyl species, which is a 17 electron species. These 17 electron species have an odd number of electrons, and they are radicals. Now, you're used to that. What normally happens when you have 2 radicals? For example, if you have H dot and H dot, what do you expect them to do? You expect them to react together to form a bond, and that's exactly what happens where sterics permit when you're dealing with organometallic compounds. So if you have an odd electron fragment, then it can dimerize to form a metal-metal bond, and in so doing, a metal-metal bond is a 1 electron donor, because essentially the compound is getting an extra electron by sharing it from another metal. So a metal-metal bond is a 1 electron donor in our covalent counting method. So if we take a classic example of this, this is manganese. And if at some point during this course I say magnesium when I should have said manganese, forgive me, point it out, and I'll correct myself. I have a bad habit of saying magnesium when I mean manganese. I've got it right this time. This is manganese. Manganese pentacarbonyl is another 17 electron fragment. It will dimerize to form a 18 electron dinuclear compound. Now, we can also increase our electron counts by using our sigma bonded ligands like chloride ligands in a bridging capacity, and this will not be novel to you. You will have seen bridging sigma ligands through lone pairs on those ligands in the chemistry, most particularly of aluminium. So you know that aluminium trichloride is not an electron deficient compound. It forms a dimeric compound with bridging chloride donating lone pairs to a second metal center. And exactly the same kind of chemistry can take place in transition metals, on transition metal organometallics in particular. So if we take a compound like this one, this is manganese pentacarbonyl bromide species here. And this will have an 18 electron count. A bromide ligand is a 1 electron donor if we were doing a covalent counting method. So this is a 1 electron donor. Manganese is in group 7, 8, 5 CO ligands makes 18. So that's a perfectly content 18 electron compound. If we heat that compound up, what happens is it eliminates carbon monoxide. So if we heat this compound up, it will lose an equivalent of carbon monoxide. Now, if you lose an equivalent of carbon monoxide from an 18 electron compound, then how many electrons will you have? 16. So this will become a 16 electron species, and we know that 16 electrons is not 18 electrons. It's favourable for it to become an 18 electron complex. How can it do that? Well, it does it in this fashion. It does it by forming bridging halide ligands. And note the way that I've drawn those bridging halide ligands. This is what I would call a normal covalent bond. A normal covalent bond meaning one of the electrons has come from manganese, one of the electrons has come from a bromo radical, and so we draw it in this fashion. This bond is not a normal covalent bond, it is a dative covalent bond, where both of the electrons have come from the bromo species and are bound to the transition metal center. So if we need to do an electron count, a normal covalent bond is a 1 electron donor, a dative covalent bond is a 2 electron donor. So if we do an electron count for this half of the molecule, then manganese is in group 7, this is a 1 electron donor 8, this is a 2 electron donor 10, and 4 times 2 is 8, giving us an 18 electron compound. Dr. Claydon often gets quite irritated when he's marking examination questions because this 18 electron rule of ours, this is a little organometallic club that we have for transition metal chemistry. It's very effective, very powerful technique, and we will come back to it over and over again consistently throughout this lecture course. It works spectacularly well for organometallic compounds. It has next to no use whatsoever in classical coordination chemistry. So it is absolutely no point in doing electron counting when you're dealing with the kind of classical coordination complexes that Dr. Claydon was talking about. It's just not any use in that context. So why is it then that this electron counting methodology is so important in organometallic chemistry and completely ignored when it comes to coordination chemistry, or completely irrelevant? Okay, so don't try using it for classical coordination compounds. Well, in classical coordination chemistry, what you have essentially is a situation where the value of delta, remember delta, what is delta? Yeah, the value of the ligand field splitting is small. And if your value of delta is small, let's see if we can follow this link. So the value of delta that we have here is small. And that means that if we start at the bottom here, we're going to fill our molecular orbital scheme with electrons, 6 electrons to here, 8 electrons, 12 electrons. Filling it up to here would be 18 electrons. But this gap is very small. So there's no particular advantage in filling these, which are essentially non-bonding orbitals, with electrons, and there's no particular disadvantage by going on beyond 18 electrons and feeding electrons into here, because the separation between these two levels is really very small. So that's what's happening in classical coordination chemistry. In classical coordination chemistry, there is nothing at all special about an 18 electron configuration, because the separation here is quite small, nothing much to be gained by filling all of these because they're non-bonding orbitals. Where you have second row transition metals or third row transition metals, or you have ligands which have very large values of delta, under those circumstances you get into the situation where this value here, the value of delta, is much larger. So where you have high-filled ligands and second and third row transition metals, delta is much larger, and so you never see more than 18 electrons. So if you have a strong filled ligand, very strong filled ligand, you're not likely to see more than 18 electrons, but these orbitals are still non-bonding. There's no particular advantage in filling them up, so you might not get beyond 18 electrons, but there's no particular driving force to reach 18 electrons either. So in the case of strong filled ligands and second and third row transition metals, you don't have more than 18, but on the other hand, there's not much necessity to actually get to 18. What we'll learn is that in organometallic chemistry, because of the pi acceptor ability of these ligands, because these ligands are accepting electron density from metal orbitals, which metal orbitals is it that are accepting electron density from? They're accepting electron density from these, which you'll recognise as being the T2G orbitals. So they accept electron density from these. And so these orbitals become bonding. That's the big difference in organometallic chemistry. The T2G set becomes bonding. And so at that point, it becomes favourable for us to fill up to this point. And when these are bonding, they drop down in energy, and this separation becomes much larger. So in organometallic chemistry, this separation is huge, and you're never going to fill the Eg orbitals, but it is favourable to fill all of the T2G orbitals. And that's what's special about organometallic chemistry as opposed to classical coordination chemistry. Class 2 are essentially high-field ligands but not organometallics, and Class 3 are organometallic ligands. The bit that tells you they are organometallic ligands is this bit, where they are good electron acceptors as well as donors. That's what's special about organometallic ligands. They have antibonding orbitals which can accept electron density as well as donating it. Now, I hate this slide. I really hate this slide because here I spent the last 40 minutes telling you that the 18 electron rule was wonderful. And indeed it is wonderful. The problem with it is that there are one or two exceptions. And those exceptions fortunately come into two main classes. The first of those classes are very early transition metal complexes of ligands that don't donate many electrons. So if you start with titanium, that's got 4 d electrons. If you have alkyl ligands on titanium, you would need an awful lot of alkyl ligands to achieve an 18 electron count. And you can't get that many alkyl ligands around the titanium. Normally in coordination or in transition metal chemistry, you are restricted to a maximum of 6 ligands. And we'll talk about that again this afternoon. We don't normally see more than 6 ligands around our metal. If we put 6 alkyl ligands around titanium, we would have a titanium hexaalkyl dianion. And that species would still, well, what would be the electron count for a titanium hexaalkyl dianion? So that's sterically the maximum number of alkyl ligands we can get round our metal. Yeah, so this species here, titanium R6, doesn't matter what R is, 2 minus. How many electrons? 12, okay? 4 from titanium, 6 from the alkyl ligands, 2 from the charge. So 12. So you cannot get above 12 in those systems because there just isn't enough room. So that's one exception where sterically it's impossible to reach 18 electrons. And you'll see a few examples like that. If you have middle transition metals like chromium through to iron, then chromium through to iron have enough electrons to start off with. Normally you can achieve an 18 electron count. There's one other class that we need to consider, and that's the square planar complexes. So those square planar complexes that Dr. Claydon will have taught you about, this is a special class of compound. And in these square planar compounds, what's happened, of course, is that dz squared is occupied and non-bonding. So what we're essentially doing is taking dz squared out of our consideration. And when we remove one of those d orbitals from our consideration in that fashion, essentially we move from an 18 electron rule to a 16 electron rule. So the kind of compounds that you've encountered that typically form square planar complexes don't conform to the 18 electron rule. They always conform to what we would call a 16 electron rule. But the reason is because dz squared, if you like, is not playing the game, not participating in bonding in the same way in these square planar compounds. Right, we just about got there. That, in one slide, is all that you need to be able to do in order to count electrons. So these slides hopefully are a useful summary. This is a profound case where this is the take-home message from this lecture.